All right, so this says use the graph of f prime that is shown. So they give us the derivative graph, which again is typically what they do, and that's good because that's the one that's going to give us all the information. I have another, like with my unit circle stick-it note, I have this on a stick-it note, and I suggest honestly you put this on a stick-it note or a scrap piece of paper too, because this is like your go-to cheat sheet for everything in Unit 5. Increasing positive, decreasing negative, same here. And where the second derivative is positive, your graph's concave up, negative means concave down. The reason I circled the f prime one is typically that's the graph that you're given, which is what happened here. So just remember, they're going to ask you questions about f, but you are looking at f prime. So you are answering questions about a graph that you do not have. So just be aware of that. But I'm going to keep this out here because we're going to use this for like every single question. So graph of f prime is shown. F is defined from -4 to 4. F of 3 equals 8. Hold on to that because that's going to come up later on. You don't need to give a full coordinate point. We're just going to give the x values. So where is f decreasing? All right, f is decreasing where the graph we're looking at is negative. That means below sea level. So that is going to be this section right here. So -4 to -3. And I know that looks like a coordinate point, but it isn't. It's an interval. So from -4 to -3. All right, where does f have critical numbers? That's where the derivative equals 0. So that's going to be right here and right here. So that is -3 and +3. Right, where does f have a local minimum? Local means relative. Minimum is going to be where the derivative changes from negative to positive. So that's below to above. So where we have a change from negative to positive is right here at -3. All right, where is f concave down? All right, look at the stick-it note. Concave down is where the graph we are looking at is decreasing. Again, we're answering questions about a graph we don't have. F, which you're not looking at, is concave down, where this graph is decreasing. So that's going to be from -1 until 3. It's where this graph is decreasing. So from -1 until 3. See how useful this is? This thing is like pure gold here, right? Points of inflection. That is where f changes concavity. So concave up to concave down or vice versa. So that's going to be where the graph we are looking at changes from increasing to decreasing or decreasing to increasing. So it's going to change from going up to going down or vice versa. So that happens right here at -1. We change from going up to going down. And then also at 3, we change from decreasing to increasing. So x equals -1 and x equals 3. And then letter F. This is a weird question. Where does f achieve its maximum value on -2 to 2? All right, so -2 to 2 is just this part. The graph is above sea level for all of that. This graph is positive for that entire time. So if f prime is positive, that means f is increasing. So that means f is increasing on the whole interval. It's increasing all the time. So where does the maximum happen? Well, if it increases from -2 to 2, like if it's going up that whole time, its maximum is going to be at the end of the interval. So at 2. It's a weird question. If it increases all the time on the interval, its peak is going to be at the end of the interval because it increased the whole time. It's like saying if you grow for your whole life, when are you the tallest? Well, at the very end of your life, like you grew the whole time. All right, and then letter G, right? The equation of a tangent line. All right, that means we need a point and a slope. And it says when x equals 3. So remember that point that I said was going to come up again? I said, hey, remember this? This is going to come up again. F of 3 equals 8. So that's our point. They gave that to us back in the beginning. Slope comes from the derivative, which, hey, that's this graph. So we want the derivative at 3. So here is 3. that point on the graph is 0. So our slope is 0. So this will be y minus 8 equals 0 times x minus 3. And I realize that all of this would be gone because it's just 0. Like this would all be gone. And you could just add over the 8 and get y equals 8. I just always like to write it in that format because that's just what we're used to doing. Oh, and someone asked, where did we get 8? They gave that to us back in the beginning. It was right here. They said f of 3 equals 8. So that was just like handed to us in the problem. They would have to tell you that because you don't have the graph of f. So they would have to just provide you that information because you don't have any other way of getting it. All right, so this one says f of x is continuous from 0 to 3 and follows the information listed in the chart. All right, we're going to be asked for all these pieces of information here, relative, extrema, inflection points. What I would do is do the graph first and then use the graph to answer the questions. I think that's the easiest thing to do. So here are the points that we can put on the graph. It's for f of x. So we're going to have 0, 0, and 1, -2, and 2, 0, and 3, 3. So I would just plot all those to start with. Those are your points for f of x. And then you don't need to worry about f prime so much. The first derivative tells you about increasing and decreasing. Well, here's the thing. You can't get from this point to this point without decreasing. And you can't get from this point to this point without increasing. So the increasing and decreasing is going to just happen. You kind of don't have to worry about that so much. So I don't really look so much at the first derivative. Second derivative, though, tells you the concavity. So we are going to need to look at that. So in between 0 and 1, our second derivative is positive. That means concave up. So when I connect from here to here, I need to be concave up. So like a smiley face. You have to bend it so that it looks like it's a right side up parabola. And then from 1 to 2, so when I connect the next 2 points, it says second derivative is positive. Again, that means concave up. So when I connect from here to here, I still want to be concave up. So you're bending it so that it's facing upwards. And then from 2 to 3, second derivative is still positive. So we're still concave up. So when you connect these 2 points, you still need to make it be concave up, which causes you to have a sharp edge there, which look, in the chart, you can't get a derivative or a second derivative at 2, and that's because of that sharp edge that happens there. So that makes sense with what's in the chart. So I'm going to use all of this to draw my graph, and then I'm going to use the graph to answer all the questions. Find the absolute maximum, and then B is find the absolute minimum. Absolutes are either critical points or endpoints. Those are your candidates, critical points or endpoints. So these could be endpoints. It's just the absolute highest or lowest point on the graph. So the maximum, the highest point on the graph happens right here. The point 3, 3. So that is 3 at x equals 3. And then the absolute minimum is the lowest point on the graph. That's going to be this one right here. And so that's -2 at x equals 1. Now, relative maximums and minimums, first of all, you can have more than one relative maximum and minimum. Absolute, you can only have one. It's absolutely the highest or absolutely the lowest. Relative maximums and minimums, you can have multiple. You can have more than one. But these cannot be endpoints. A relative extreme cannot be an endpoint because an endpoint isn't relative to anything on the other side. Relative or local maximums and minimums cannot be endpoints. It has to be somewhere within the interval. So a relative maximum, that's going to happen when the graph goes up and comes back down. And there's no place that happens on this graph. This graph does not ever go up, have a peak, and then come back down. So there just are none. And a relative minimum, the graph is going to go down and then come back up. So where that happens on this graph is right here. So -2 at x equals 1. You might be like, hey, Miss Cole, that was the absolute minimum. That's okay. It can be both. And then lastly, inflection points are where we change concavity. But this graph never did. It was concave up and then concave up and then concave up. It never changed concavity, so there aren't any. An inflection point is where that changes, and it never changed, so there just aren't any. But that's a cool looking graph. I like that. All right, so this is what curve sketching is. Sketch a graph with the following characteristics. So they're going to tell you some information, and they're going to tell you about the derivatives, and then you have to take that and put it together and draw a graph. So vertical asymptote at 1. And horizontal asymptote at y equals 2. And the horizontal ones, I only just do those at the edges because it could go through in between if we needed it to. Just needs to level off at the edge. All right, and then here's the information about the derivatives. First derivative is negative for x less than 1. All right, if your first derivative is negative, what does that mean the graph should be doing? So first derivative is negative. Look back at the little cheat sheet that I gave you. Derivative is negative. Good, perfect. Nice job, everybody. All right, that means the graph should be decreasing. Sweet. All right, so we want to be decreasing for everything smaller than 1. So everything on this side of the asymptote, I need for the graph to be going down. So it's going to need to be doing something like this. And then this says derivative is positive for everything after 1. So if derivative is positive, that means the graph should be increasing. So I want to be increasing for this side. So that would look something like that. All right, number 5 is the same kind of thing we did with number 1. So we're going to go through this whole process again. I'm not going to make us write the justifications for the sake of time here. So we're going to get all this information and then sketch the graph. So we're given this function written this way and in a factored version, which is nice to have it in both formats. So letter A says find the roots. Roots is another word for zeros. So that would just be where these factors are 0. So that would be at -1 and 2. And I'm going to plot the points on the graph just as we get them. I'm going to have zeros at -1 and 2. So I'm just going to go ahead and put those on there. All right, critical points. That's derivative equals 0. So I'm going to look at this version of the equation to get the derivative. That's going to be easier. You'd have to do a product rule, and that would be all crazy. So let's look at this one. So derivative is 3x squared minus 6x. Set that equal to 0. Factor out 3x. You're going to have x minus 2. And so you get 0 and you get 2. And those are critical points no matter what. You don't have to test anything else. They just are critical points. All right, relative extrema. I'm going to need to make a number line using these two factors. So for the 3x and for the x minus 2. So 3x has a critical point at 0, x minus 2 at 2. They're going to be negative and then turn positive. And so when you slice up this number line to get the overall sign, it's going to be positive, negative, positive. And so at 0, we have a change from positive to negative. So what does that mean, guys? If we change from positive to negative, that means relative what? Awesome, good, maximum, relative maximum. All right, so we're going to have a relative maximum is not 0. You have to take 0 and plug it back into the function. So if you plug in 0, you're going to get 4. So a relative maximum is 4 at x equals 0. And I'll go ahead and plot that. And then at 2, we have a change from negative to positive. So that means relative minimum. So relative minimum is not 2. You have to plug 2 back in. So if you plug in 2, 2 cubed is 8. 2 squared is 4 times 3 is 12. So we'd have 8 minus 12, which is negative 4, plus 4 is 0. So 0 at x equals 2. And I actually already have that on the graph because that was one of the roots since it was 0. All right, points of inflection. This is the new stuff. We're going to do second derivative equals 0. So I'm looking back at the first derivative, which is right here. So the second derivative will be 6x minus 6. And I'll go ahead and divide out the 6 this time, since someone had brought that up last time. If you divide out 6, you're going to be left with x minus 1. And so we get 1. But here's the thing. You don't get to just assume that's an inflection point. You have to check it first. So I'm going to make a number line for this, but it will change. It'll be negative and then turn positive. So this is, in fact, an inflection point. We have concave down and then concave up. Now I want to plot that on the graph as well. So I need to take 1 and plug it back into the function to see where I'm going to plot that point. So if I plug in 1, let's see, that'll be 1 minus 3. So negative 2 plus 4 would be 2. So the point 1, 2. And so what we're going to do is just connect all these points. And we just need to do the correct concavity. So we want to be concave down and then change to concave up. This second derivative changes from negative to positive. So concave down until we get to 1, which is right here, and that's this point. So we're going to be concave down for this part. So down like a frowny face, like it's bending downwards. So concave down, and then at this point 1, it's going to change to concave up. So this should be concave up for the rest of it. And so this is the point where that change happens. And then I'll just have time for this last one here. Number 6, it says a differentiable function has the following information, right? So let's read through this and see what we've got. F of 3 equals 7. All right, cool. That just means you have the point 37 somewhere on the graph. That's what that's telling you. The point 37 exists on the graph. That's all we can get out of that. All right, then they tell us the derivative at 3 is 0. All right, hey guys, if the derivative equals 0, what do we know about this point? If the derivative is 0, then it is perfect. Nice job. That means it's a critical point. Nice job. If the derivative is 0, then it's a critical point. All right, cool. And then the last piece of information we have the second derivative at 3 is negative 4. Here's the thing that people get caught up on this is that it's a negative 4. It could be a negative 5, it could be a negative 17, it could be a negative a half, it could be a negative a million. Don't get hung up on the fact that it's a 4. It's just the fact that it's negative. If your second derivative is negative, what do you know about the graph? If the second derivative is negative. Good, nice job, concave down. Second derivative is negative, concave down, it's gonna look like this. All right, so what conclusion can we draw from this? We have some point, it's a critical point, and the graph is concave down there. So if the graph is concave down, what do we know about this critical point? What can I label that as, or what can I say about that critical point? Good, nice job, relative maximum. If your graph's concave down and you have that critical point, it's gonna have to be at the peak of the hill. So we're going to say 3, 7 is a relative maximum.